All right. Now, let me go over one problem, okay, first. So we're going to do the triple integral, and this is a z squared over x squared plus z squared and dv. Now, what is the E? Okay, E is a domain described by the following inequalities, okay, and z equal between y and 4, and x is between 0 and z. Okay, this is pretty complicated. Yeah, description. It's hard to draw it, honestly. Okay. So this description, let's try to sketch the graph because that helps us to set up the iterative integral for this. Okay, y is between 0 and 4. Okay, so this could be, yeah, this whole line, okay, between 1 and 4. Okay, 1 and 4. Okay, so for any arbitrary y, okay, and your z will be between y and 4. Okay, so z is between 1 and 4. When z equals y, this is a line. Okay, so that means z is always between y and 4. Okay, so this line segment will be in a solid. Okay, so that means this triangle will be portion of the solid. Okay, right? Y between 1 and 4, and z is between y and 4. Okay, that's a 4. Okay, and then how about x? X is between 0 and z. Okay, that's a problem here. Between 0 and z. 0, when x equals z, this is a good midline. Okay, passing through that. Okay, so there's no restriction on the x. Okay, no restriction on the y. So let's try to, yeah, x equals z is this plane. Okay, x equals z is this plane. So for any point in this triangle, okay, for any point in this triangle, I call it, yeah, this is D, for example. For any point in this triangle, x, y, and z, okay, your x value is determined by z, okay. So higher and x get larger. When z is getting larger, x is getting larger. So this is a line segment, okay. So imagine the picture I got here. Yeah, it's going to be yeah, it's harder to draw the solid, but those are the lines in the solid. Okay. Okay. So how can I set up integral? I can call this one as a D. Okay. D is going to be in the y-z plane, and y is between 0 between 1 and 4, and this is a triangle. This is between 4 and y. Okay. Okay. So for each point yz in D, my x value is between 0 and z. Okay, so this is you can view it as a graph over D. Okay, the function of the graph is the function of graph is just f of yz equals z. Okay, so you can use it like a double derivative. Okay, and this is a dA. dA is dy dz, and for each point yz, right, your x value will be between 0 and z. Okay, so dx. All right, So that's it. So first of all, you have to evaluate this single integrals. Okay, evaluate this single integrals. Now, I have to say that there's a formula for this integral. You remember, if we have 1 over a squared plus x squared dx, and that would be 1 over a arc tangent x over a plus constant. Okay, so here a is a z. Okay, so that means I have a antiderivative. H is z squared over z, right? Because z squared taken out, and the arctangent x over z, right? Evaluate to two endpoints dA. Okay, so let's evaluate this, and I got here's a z. Okay, so arctangent, when plug z for x, is arctangent 1 minus arctangent 0, okay, dA. So then you simplify. Arctangent 1 is going to be pi. It's going to be pi over 4. Okay, arctangent 0 is going to be 0. Okay, so now you have this double integral over this is y and z over this triangle, right? Over this triangle. Then you can use any iterative integrals. Okay, so you can still use and dy. Y is between 0 between 1 and 4, right? Y and between 1 and 4. For each y and z values is between y and for each y, the z value is between y and 4. Okay, then you find the antiderivative of this. It's going to be pi over 8, I think, and z squared. Okay, so y and 4 here, dy. Okay, so let's get, we'll get pi over 8, we take it out. This will be the integral from 0 to 4, and 4 squared minus y squared. This is a 4 squared minus y squared, yes, dy. And then we find the antiderivative of this. The antiderivative is 4y squared y minus half of y cubed. Okay, you just plug 4 for, yeah, that's 4 cubed minus half of a 4 cubed. So you get half of a 4 cubed, right? Yeah, you get half of a 4 cubed. No, 3. 1/3. Okay. So you will get, yeah, then you simplify, right? Yeah, you simplify it, you get pi 4 cubed of 8 and times 2 over 3. Okay, so then you simplify it. Okay. Evaluate. Wait a minute, did I make mistakes? I think I made mistakes here because this is the integral is from 1 to 4, okay? From 1 to 4, so I have additional terms here. Yes. Yeah, so it's pi over 4 and 4 cubed minus 1/3 4 cubed minus when it's 1. Okay, it's a little bit complicated. Okay, so you can simplify it, and let's finish this. So it's going to be 2 over 3 4 cubed minus this is minus 4 squared Right. So anyway, what is this? Okay. So this is going to be 4 squared taken out. Yeah, 4 squared taken out, then 2 times, yeah. And actually this is going to be pi over 8. I take a 4 square out. And I have 8 minus 3, so 5 over 3 plus 1/3. Okay. Let you simplify. Okay, I'm not going to continue this. This will be, yeah. Okay, let's finish it. Okay, so 16 times 5. 16 times 5 is 30, then it's 80. 80 plus 181. 81, right? When they divide by 8. Okay. 81 divided by 3 is going to be 27. So it's 27 pi over 8. Okay. So that's the now we're going to talk about substitutions. Okay. Substitutions, let's go to let's understand the formula. The substitution, we remember, see, in dimensional 1 case, okay, if you have an interval, okay, here's A and B. If I have the integral over this, is going to be, this is variable x, right? I have an integral from A to B f of x dx. The so-called substitution is I have another interval, here's alpha beta, and they have a map. And let's say x is going to be h over t, for example, right? Okay, when h over t, then and also we assume, just make it simpler. A is going to be h of alpha, right? B is going to be h of beta. So then in this case, the derivative is positive. Okay, so so you have on left hand side, right hand side, you have this, right? You just replace x by h of t, and dx is going to be h prime t dt, and this is from alpha to the beta. Okay, so you do have this. Okay, now in some cases, h prime t is negative if you if h alpha is b, you know. Okay, so it's reverse. So in this case, h prime is going to be positive. So this is going to be the derivative, okay, of the map actually. But and in two-dimensional case, okay, a little bit more complicated. In two-dimensional case, you have yeah, there's the orientation problem here, you know. So in two-dimensional case, you have a domain D, right? And you have a function x and y. So you have a double integral, right? Okay. So how do you, what kind of substitution are you going to use? Well, you have U and the V, and here usually is a much better domain called D prime. Okay. So there's a map. Okay, send this better region to over to that region. So x is x uv, y is y uv, depends on u and the v. Okay. Then, okay, then this double integral can be become a double integral over this beta region. So here f is replaced by this becomes uv function. Okay. Now the difficult part is what is derivative here in the place of derivative h prime, right? H prime have to be the absolute value of the determinant, okay? Partial derivatives. So the derivative of a mapping will be the determinant, okay? Okay, then will be du dv here, so just the dA prime, okay? So that's there is a similarity here, right? Now you have to put that absolute value. And now why there's no absolute value here on the top? Because that's a little bit tricky here. Okay. Yeah, it depends how do we express this single integral. Yeah, it's hard. There's an orientation problem here, so we don't want to. Yeah, if we write interval, if we write the integral in this form, yeah, yes, you have to put an absolute value. Okay, and there's absolute value here. So it depends on the sign. Okay. Okay. Yeah, let me mute my phone. Okay, so no sound. Okay, so this is a formula. So, and the high dimension is similar. Just to get the absolute value of a determinant of a matrix, 3 by 3 matrix. Okay. All right. So let's take a look at the following example. Okay. Here's the example, right? So you have a sector in the space, okay? And this could be just one portion of that, you know. All right. So this is a D. It's easy to describe, right? So this is and the distance from here to here is a beta. The distance from here to here is alpha. Then you also have a interval, theta, right? Theta could be, you know, this theta 1, and here another theta 2. Okay, so this is a sector. Okay. And you have a double integral of the function over that. Okay. Then the transformation you're going to make is r cosine theta, y equals r sine theta. If we use that, and clearly the domain you're going to have here, the pre-image we call, is going to be r is between alpha and the beta, right? Theta is between theta 1 and theta 2. Okay, so you will get a rectangle. So it's much better domain, right? Yeah. Okay, so this is a D prime. And this D prime is mapped to this portion of the sector. Okay, so therefore, this integral becomes D prime of f r cosine theta, r sine theta. Now, and this r here is actually nothing but the determinant, okay? So you can look at the determinant of this matrix. Okay, the determinant of this matrix is going to be the partial derivative of x with respect to r, partial derivative of y with respect to r, and partial derivative of x with respect to theta, partial derivative of y with respect to theta. Okay, so put the determinant here, det. Then, when you differentiate, you get cosine theta, you get sine theta, right? Then you have again a negative r sine theta and r cosine theta. Okay, so how do you calculate determinant? Just cross product, right? It's r cosine square theta minus negative r sine square theta. And then when you do the calculation, it's going to be cosine square theta plus sine square theta, which is just equal to r. This is the way it's r from, okay? Okay, so the absolute value is still r. So that's why how do we get this integral in polar coordinates? Essentially, we actually we have a transformation. Okay, so the domain D is a pre-image is the image of a rectangle. Okay, we'll use the okay. Okay, this is just an example. Okay, a very good example. Now the next problem, we are not going to deal with polar coordinates. Okay, 3-dimensional case, we have a spherical coordinates, cylindrical coordinates. Those are the transformation. Okay, actually. So now here R is bounded by y squared equals 4 minus 4x squared, and y squared equals 4 plus 4x. Okay, and the y is going to be greater than or equal to 0. Okay. Okay, so we are going to evaluate this y with respect to this double integral. Evaluate this double integral. First of all, you have to draw the picture. Okay, you draw the picture. So this is a part of the parabola. Okay, x is going to be we have to figure out, right? So this is another parabola. Okay, so this is actually is you can write in the following way: x equals quarter of y squared minus 1, right? It's the same as y squared equals 4 plus 4x. Okay, and this will be consider x equals a negative, right, and plus 1. Okay, so when y is it opens downward. Okay, it is opens downward. Okay. Okay, so that is parabola opens downward. Not downward, to the left, right? And went to the right because y is a square, x is just 1 variable. So this is a domain. Okay, question is how do you evaluate this domain? Okay, and we can try different ways to do that later. Okay, let's set up an integral. Okay, let's set up an integral. There are 2 different ways to set up an integral. Okay, there are 2 different ways to set up an integral. Okay, so this is when y equals 0, this is -1, this is positive 1. Okay, so how about this point? When x equals 0, I think that should be 2. Okay, that should be 2. Okay, when x equals 0, the y value is 2. Okay, so this is the intersection point. Now let's set up 2 iterative integral. Okay, so for each x between -1 and +1, right? Then the y value is between 0 and some function. That function depends on it depends on the x, okay, location of x. Okay, so actually this is going to be square root of which one is on the left, right? Which is when x is negative, okay? When x is negative, okay, when x is negative, you will get this one, right? You're using the vertical lines, okay? So you have to use this one. So it's y is going to be square root of 4 plus 4x, okay? when x is positive, you use that piece, right? So it will be square 4 minus 4x. Okay. So now it's piecewise defined function. So the double integral is going to be from x term -1 to +1, and then you have to put a question mark here. You don't know what is that, right? So y dy and dx. So it will be iterating. You have to use two integrals from 0 to this, then from -1 to 0 when x, then you get 4 plus 4x. Okay, and from 0 to +1, it will be from 0 to 4 minus square 4 minus 4x. Okay. So this is a two iterative integrals. Okay, it's not too bad when you evaluate. You can do that. Okay. For example, this will be antiderivative will be half of y squared. Then you evaluate this two and the point. And here, the antiderivative is half of y squared. Okay, so let's finish it. It's not too bad, right? So it's from the -1 to 0, and the 4 plus 4x when you divide and divide by 2, you get 2 plus 2x, right? 2 plus 2x. And here, you get also 2 minus 2x, okay? Because 4 minus 4x divided by 2. Okay, then you have to find the antiderivative of this first function, 2x plus x squared. And this will be 2x minus x squared, okay? And let's complete it. The first one is 0. It's minus 2 to the -1 plus -1 squared, right? Yeah. And here we 2 times 1 minus 1 squared minus 0. So let's finish this. -2 plus 1 is -1. -2 plus 1, yeah. And the plus 1. So answer is 2. Okay, the answer is 2. Now, this is a little bit complicated, right? When you have to, break the integral into two parts. Okay. Now, what happens if you use horizontal line segments to set up an iterative integral? That's probably much easier. So let's go back to Okay. So this equation here is y squared plus 4 plus 4x. That equation is y squared equals 4 minus 4x. Okay. All right. So now I'm going to do the following for each y between 0 and 2. I want to get the upper bound for yx and the lower bound for x. Okay. The lower bound for x is determined by the parabola opens to the right. Okay. So that will be quarter of y squared minus 1, right? The other one will be, you solve for x, you get a negative quarter of y squared plus 1. Okay, so it's determined by those two, upper bound and lower bound. Okay, so this double integral dA, right, can be treated as iterative integrals. It's negative a quarter of y squared minus 1, negative quarter y squared plus 1. Here's the y and the dx. And this y is independent of x, so you can take it out. Just y. The antiderivative, so you take the difference, right? As the top one minus the bottom one. So a quarter of y squared plus 1 minus a quarter of y squared minus 1, okay? Okay, then you simplify it. So you will get you get 2 minus a half of y squared. Okay, so you get the integral of a polynomial. That's easy, right? So it's 2y squared minus half of y cubed. Then find the antiderivative of this function. It's 2, no, 2, just 2y, not 2y squared. So you get the y squared minus a quarter. So 1/8 y to the 4th power. Okay, evaluate to end point. So you get 2 squared minus a quarter of 2 to the 4th power. That's it. So you have a 4, then you have a 2. So the answer is still 2. Surprised, right? All right. So I'm going to do this problem in a slightly different way. Okay, let's try this. Okay, this is okay, this is y squared plus equals 4 plus 4x. Here's y squared equals 4 minus 4x. Okay. Now, yeah, I'm going to consider, don't ask me how to get this, right? I'm going to consider this transformation. Okay, sometimes it's given. Okay, I want to see, this is D. I want to figure it out under this transformation. Yeah, what is the pre-image of that domain D? Okay, what is the pre-image of that domain D? Okay, this transformation can you figure out the domain D prime? Okay, so let's see. Yeah, it's a little bit difficult to figure it out, right? So for this, trying to figure out the pre-image. Okay. X is u squared minus v squared, y equals 2uv. Okay. So how do you get, first of all, let's see, how do you get y equals 0? This is like we want to determine the edges. Okay, these edges. Okay, And this h, yeah, let's look at y equals 0 if and only if u 0 or v equals 0. So u 0, v equals 0, that's u and the v. Okay, u 0 or v 0. This is the two sides. Okay. Okay. So those two sides are sent to here. Actually, send it to the portion of the x-axis. Okay. Then you will see that. Okay. Then you see that x. Yeah. Then you see that when x equals when u equals 1. Okay. When u equals 1. Yeah, let's see what is this h, where from this h, right? This is this portion of that coming from actually from here. Okay. Okay. So how do you see that? Well, when u equals 1, v equals an arbitrary, right? V equals, so when u equals 1, okay, when u equals 1, okay, so x is going to be 1 minus v squared. Y equals 2v. Okay. So what's the relationship between them? Okay. The relationship between them will be y squared equals 4x plus 4. Okay. So this is a y squared equals 4x plus 4. Okay. Yeah, because it's a 4v squared and it's a 4x. Okay. Yeah. It's minus, yeah, it's minus, yeah. Okay, so it's minus. Okay, so this side, let me mark it. Okay, this side corresponding to this side. Okay, yes. And then you look at the case when v equals 1. When v equals 1, x is going to be u squared minus 1, y equals 2u. Okay, so that means y squared equals 4 plus 4x. Okay, so this side, yeah, this side is sent to here. Okay, so imagine, let's say this domain, okay, is sent to this domain. Okay, so the idea is actually just close up this side. Okay, close this side, these two sides, make it flat, and you get that picture. Okay. All right. So understand. Yeah, this is a square, and other side is I cannot tell the name of that. Then so the double integral over the double integral function over that domain is going to be the double integral of the square, and the y is going to be just 2uv, right? That's the y, and then you have to find out the determinant of the derivative, right? So two-dimensional derivative. So determinant of xy uv dA prime. Okay. So let's calculate that. Let's calculate what is this, right? So this is going to be the determinant. Is going to be let's put a determinant. So the partial derivative of x with respect to u, partial derivative y with respect to u, partial derivative x with respect to v, partial derivative y with respect to v. Okay. All right, so partial derivative of x with respect to u is 2u. Partial derivative of y with respect to u is 2v. And then your partial derivative of x with respect to v is 2v. And the partial derivative of y with respect to v is 2u. Okay, so the answer will be, the determinant will be 2u squared minus v squared. Okay, so the double integral y dA is going to be 2uv, and have it another 2 here, right? U squared plus v squared dA prime. Okay. All right, so you multiply this out, and you have a u cube v plus uv cube dA prime. Then this is a unit square, right? So it doesn't matter which one is first. Okay, and you can say u first and v second, right? That's fine. So then you evaluate this, find the antiderivative with respect to u. So it's u to the fourth power v plus 2u squared v cubed. Evaluate the two endpoints. And you will get v and 2u cubed. Okay. Then you find an antiderivative of this, and that is going to be, yeah, let me double check, okay, if any computation mistakes or not. Okay, I have yeah, I have a combination mistake here. It's a 4. Okay, 4 times 4. Okay, so that will be 8. So this will be 8. Okay, so anyway, that's a double 2 here. Okay, so I don't forget this. Okay, so the antiderivative is going to be v squared and the v to the fourth power. Okay, and the evaluate to end the points. That's the answer is 2. Okay, then it's correct. Okay, still get the same answer. Okay, of course, you will say that, well, it's so hard to find out this transformation. Okay, now you are given the transformation this time. Okay, even given the transformation, it's harder to find the pre-image. How do you determine the pre-image? I use just look at the boundary. Okay, the boundary. How can you, yeah, which line is sent to this parabola, right? Okay. The next problem, we have to find the transformation. Okay, this is a problem from number 24. It's a typical problem. So evaluate the double integral x plus y e to the x squared minus y squared dA. Now, what is r? R is a rectangle. Okay, enclosed by the lines. Okay, those are lines. X minus y equals 0, x minus y equals 2, x plus y equals 0, x plus y equals 3. Okay, equals 3. So I have yeah, can you draw this 4 lines? All right, so x minus y equals 0 is this line. X minus y equals 2, I think is this line. X plus y equals 0, this line. X plus y equals 3 is this line. So this is my rectangle. This is my rectangle. Now, the good part is the transformation is easy to find out, okay? Why? Because for an arbitrary point, this could be the intersection of these two lines. And this line will be x minus y, let's call it u, okay? Right? And this line will be x plus y, we call the v. Now, so this line u equals 2, this line u equals 0, right? It's like, and this line v equals 3, this v equals 0, okay? So actually, if you let u to be x minus y, v to be x plus y, okay? Then you can solve it, you can solve for x equals half of u plus v, and the y equals the second equation minus the first equation, so v minus u, okay? Half of that. Okay, so this, the pre-image is u is between 0 and 1, 0 and 2. V is between 0 and 3. So this rectangle, okay, under the transformation will be sent to here, okay, right? So when the value u changes, you get family of lines, right? When the value of v changes, you get family lines. So the intersections, right, gives all the points in this rectangle. So the range, the domain, the range for u is from 0 to 2. The range for v is from 0 to v. From 0 to 3 is the range for the v, okay? All right, so that's it. This is we figured out this, right? So now, okay, now this double integral of that region R, okay, over in the x plus y e to the x squared minus y squared dA, okay, is going to be, okay, is going to be the integral of d prime, and I have to change x plus y. See, x squared minus y squared. So right, so this is a dA prime, and this is will be will be some function. Okay, you have to put something here. So let's figure it out. And you have to have a determinant. This part is determinant, absolute value. This is a part of the function. Okay, so this will be f. This will be the absolute value of the determinant. Okay. Okay. Right. So let's do the calculation. So determinant of this matrix, okay, is going to be determinant. The partial derivative of x with respect to u is 1/2. The partial derivative of y with respect to u, negative 1/2. The partial derivative of x with respect to v, 1/2. The partial derivative of y with respect to v is going to be half. Okay, so it's going to be 1/4 minus negative 1/4. So it's going to be 1/2. It's good number. Okay, So 1/2. Okay, but we know that x plus y is already know that x plus y is v. Okay, how about x squared minus y squared? Xy minus y is x minus y, x plus y, right? So x minus y is u. X plus y is v. Okay, so it will be v e to the uv. Okay, great. So now you just needed to yeah, okay, so I do what kind of notation I use? If you use R here, then I use R prime. Okay, yeah, use R prime. So this integral e to the x squared minus y squared dA is going to be the double integral. And this will be v e to the uv. And it's 1/2 and the dA. Okay, dA prime. So now you can write us in any form, right? If you use a u first, and the v is from 0 to 3. Okay, or it's from v e to the u, right? And the du and the dv. Okay, it doesn't matter which one is first. I think then you can always evaluate this integral. Okay. Okay. I think because the second one is better. You see, if you deal with, if this integral with respect to u, v, and have a v outside and have a v in on the e, right? So I think it's more complicated. So the second one is better because the antiderivative, yeah, let's use the second one. That's why I write down 2 of them here. So the antiderivative of v e to the uv with respect to u is just e to the uv, okay? Because when you differentiate with respect to u, you get a v times e to the uv. So then evaluate 2 endpoints, and then you will get e to the 2 v minus e to the 0. Okay. Then you find the antiderivative of this function with respect to v, either 2v minus v, right? Okay. Then my answer is e to the 6 minus 3, half of e to the 0 minus 0. Okay. Right. So, right. Yeah, let's double check. So I don't see anything wrong here. So that's going to be half of e to the 6 minus, yeah, use one fraction. It's 7 over 2. Okay, so that's it. Okay, let me check if any good problems I don't need it. I probably don't have time to evaluate, but let's try to see how do we set up the integrals. Yeah, let's go to section 15.9. Okay, I did not discuss triple integrals here. Yeah, that's problem number 24. And sometimes you are given the transformation, okay? Then you don't need to worry about. Probably just need to determine the domain using that transformation. It'll be much easier than you construct the transformation. Okay. Yeah, the other like strict coordinates already. If you look at my lectures, I already mentioned how do we get use a substitution, the special substitution. Yeah, and to get the formula. Okay, let's try to do number 6, 26. Okay, so we are we're going to evaluate sine 9x squared plus 4y squared and this double integral. Okay, where I is the region. Okay, in the first quadrant bounded by ellipse 9x squared plus 4y squared equals 1. Okay, so 9 squared, let's draw the picture here. 9 squared plus 4y squared equals 1. Okay, so how does the parabola look like? Ellipse look like? Okay, so if you use, you can also express like x squared over 1 over 3 squared, y squared over 1/2 squared equals 1. So which one is longer? Under the y, 1/2 is large. So I think it's ellipse looks like that. Okay, it's not a big deal. Okay, so it's not a circle, but it's almost a circle, right? So you can, it's very natural to construct a transformation similar to the polar coordinates. So you will get x equals, x over, instead of, let's see. Yeah, you have to construct a transformation in order to evaluate this integral. Okay. So an arbitrary point here inside, right? You will get so what I'm trying to do is you get 1/3 of rho r cosine theta. Okay, y equals 1/2 of r sine theta. Okay, so the idea is that for every small ellipse, right? So the r is going to be small, right? So when you square it, okay, when you square it, you will get 3x squared plus 2y squared equals r squared, right? So r should be less than or equal to 1 because the inside ellipse. Okay, and then theta, so r is between 1 and 0, and the theta is between 0 and 2 pi. So what do we have here? This is r prime 1, and this is a theta from 0 to 2 pi. This rectangle is sent to that ellipse. the domain region enclosed by the ellipse. Very similar to the polar coordinates. The only difference is here you divide by 1/3, 1/2. Okay. All right. So this is so now this double integral, right, of f dA is going to be r prime f. You can have you can have 1/3 r cosine theta, 1/2 r sine theta, and this will be something here, dA prime. So you have the determinant of these derivatives. Okay, so we have to calculate. We don't know. Probably it's multiplied by some numbers, right? So determinant of this is very similar to polar coordinates. It's going to be 1/3 cosine theta, and then here 1/2 sine theta. Then you differentiate with respect to theta and differentiate with respect to theta. So it's cosine theta. But when you multiply this out, it's just 1/6 and r. Okay, 1/6 of r. So that's just because it's a cosine square. Yeah, this common factor is 1/6. Okay, 1/6, cosine square theta, and the minus, so minus 1/6 r and the negative sine square theta. So add them together, just 1/6 r. So now it's clear. Okay, so the double integral of this function, sine 9x squared plus 4y squared dA, it becomes r prime, and 9x squared plus 4y squared is going to be just r squared. Okay, so actually this is just the sine r squared. Okay, and then you have absolute value of 1/6 r. Okay, so that's the dA prime. Okay, all right, that's it. So this is going to be double integral. You can write as triple integral, right? Okay. Well, you have to use a substitution to evaluate. Okay. So you let u to be r squared. So du equals 2r dr. Okay, then this integral will be u is r squared. So when I is 0, u is 0. When I is 1, u is 1. And here sine u 1/6. So I have to divide by 2, so it's 12 du. Okay. So the answer will be just the sine 1. Sine 1 has no, we don't know the value exactly, right? Okay, and then d theta. Because sine 0 is 0. Okay, so the answer will be 12 pi over 12, 2 pi over 12 sine 1, which is a pi over 6 sine 1. Okay, so that is the answer. Okay. Yeah, remember, maybe I will test, how to find a substitution for the region enclosed by ellipse. Okay, so in general, if you have if they have the region enclosed by ellipse, hold on, I think there is a small mistakes here. It's in the first quadrant. I'm good. See, if it's in the first quadrant, and my theta is only pi over 2. Okay. Yeah, the theta is pi over 2. So I have to constantly modify. See, at the end, double check your work. Okay. At the end, you should double check your work, and Otherwise, you know, it's easy. You don't make a mistake. I just realized that, you know, at the end, I just look at the problem. Did I do it correctly, right? And then I can correct the mistake. Yeah. Okay. Okay. So is yeah. Let me check my pen for a minute. So we needed to learn how to set up, how to find the transformation. Yeah, substitution, whatever. For integrals, how to find the substitution for the integral over an elliptic region. Okay, over an elliptic region. Okay. So this will be pi over 2. Yeah, pi over 2, pi over 2, pi over 2. And this will be pi over 2, so it'll be pi over 24 sine 1. Okay. So here's the equation: x squared over a squared plus y squared over b squared equals 1. Okay. So the standard transformation will be x equals a times r cosine theta. Y equals b, a sine theta. Okay. Then x squared over a squared plus y squared over b squared equals r squared. So r squared, say I is going to be less than or equal to 1. Okay. You're right. Yeah, the antiderivative of a sine here is negative cosine. Okay, that's another place. Let me double click, change it. So antiderivative of sine is going to be cosine, negative cosine u, right? So it would be, but the cosine 0 is 1, so it's 1 minus cosine 1. Clear? Yeah, it's evaluated at the two ending points. Yeah, so this will be 1 minus, so it's going to be pi over 24, 1 minus cosine 1. Oh my God. Okay. All right. So, so this is a x squared over a squared plus y squared over b squared equals r squared. So for a point inside the ellipse, I is going to be less than 1, right? Right? I is going to be less than 1. Yeah, this is r, right? I is less than 1. So you can for the whole ellipse, I is less than 1, greater than 0, and theta is less than 0, greater than 0, less than 2 pi. So that is my standard domain. Okay, okay, which is sent to here by this transformation. Okay, so if you are given a elliptic region, remember it's almost similar to the substitute, polar coordinates. Okay, and the only difference is you multiply by a, multiply by b, these two terms. Okay, so there'll be two type of regions you should pay attention. Another type of region you have to pay attention is a rectangle determined by two pairs of parallel lines. Okay, not rectangle, it's a parallelogram. Okay, the parallelogram, this one, this one is a family of ax plus b, y equals u, and this will be like cx plus dy equals v. Okay, then you will get a rectangle here, which is sent to send it to this. Okay. Yeah, this is a two type of transformation we needed to pay attention. Okay, if this one u equals let's say u equals I'm going to choose a bound for that. Okay, let's assume just u equals u0 and that's u equals u1. Okay, and this will be v equals v0, v equals v1. Okay, then you have here v0, v1, u0, u1. So this will be transformed to that parallelogram. Okay, so then you can calculate, you can solve for x and y. Okay, in terms of uv, then you can translate the double integral of r to a double integral of r prime. Okay. Okay, so you have a double integral of r. This will be the double integral of r prime. But then be careful, you have an absolute value here of the determinant. Okay, this will be a constant in general. Okay, okay. You can calculate so that's it, and we have to stop here.
Professor, I have a question for you.
Hold on.